In this session, we want to implement the subroutine and the input files explained before to analyze the results. We put all the input files and the subroutine in a folder. Next, we need to create a file to run input files and subroutines outside the graphical interface. Because some keywords don't have any GUI-related command. Also, we are using the *restart command in our files and it's not applicable in the GUI. To create this file, first create a text file. Open the text file and type these lines: cmd.exe and iportwars.bat. Note that import lines is for calling the port run. After that, change the file extension from .txt to .bat. We have created this file before, so we delete the redundant file. Double-click the .bat file. As you see, you can apply the commands in the current work directly. To run the input files without the subroutine, you need to type this line: Abaqus job equal. After the equal sign, you must type your input file's name. The first input file is the axisymmetric model. To add the name correctly, copy the file's name and paste it here. Then click the Hit button. First, the port run is activated, which was the linked before with the Abaqus. Then the Abaqus will open to send the input file for the solver to run the file. Pay attention to the folder. See, some files are created. Remember, as long as the .lck file exists, the input file is still running. When the .lck file disappears, the analysis is completed. Now you can see the .lck file disappeared, which means the first analysis is completed. Press the keyboard's up arrow so you don't have to type the command again. This time we run the second input file, the revolve model. Copy the name, delete the previous one, and paste the new name. After hitting the enter, the analysis should ask you the old job name because it needs the previous job to run the new one. So you could copy the previous job name from here and paste it here. After pressing the enter button, the solver starts to run the job. Like before, we must wait till the .lck file is deleted. Until then, we make the preparations for the next analysis. The next input file is the reflection model. So we copy the file's name and paste it here, then wait till the current job is completed. Take a look at the .odb file. Its size is rising during the analysis, as it should be. Note that the analyses we have at this time are not including the subroutine. We will tell you what command you should add to the command window to run the files with the subroutine. Now the job is completed because we don't have the .lck file, and by clicking the enter, we run the next input file. If you encounter this line, the input line is too long, you have to close the current window and open a new one. Now we type the command again, insert the file's name and press the Enter. Again, it asks us for the old job name, the Revolve model. Copy the name and paste it here, then hit the Enter. Now we have to wait until the reflect analysis is completed. The analysis uses the previous results with the *restart command to complete the process. Now let's run the next input file, the rolling model. Copy the file's name, delete the last, paste the new name, and hit the Enter. Again, it will ask us the old job name, which is the reflect model file's name. Now we wait till the job is completed. Note that we are running the input files respectively. First, we run the axisymmetric model, and then the revolve model was analyzed. The last one was the reflect model, which the whole model was simulated, and now we are running the rolling model. This one analyzes the model as a steady state model. Remember, all files were explained before. Next, we are going to use the UMesh motion subroutine in two analyses, one with slip and one without it. Now let's run the file without the slip. Copy the name and paste it here. Next, we need to implement the subroutine. Type user equal, and after the equal sign, we have to insert the subroutine file's name. Copy the name and paste it here. Then click the Enter. Again, we encountered the error, so we have to close the current window and open a new one. We type the command, copy the file's name here, and then insert the subroutine file's name. After pressing the Enter, it will ask us the restart file because we have the *restart keyword in our file. Which is the rolling model file's name. Now we wait until the job is completed. This one will take a bit longer. Now let's run the last input file, which is the one with a slip and uses the subroutine. Like before, copy the file's name and paste it here as the job's name. Here, insert the subroutine file's name. The restart file would be the rolling model file's name. Now, we wait until the analysis is completed. Now, let's see the results of the input files that we ran. First, we open the ODB file for the axisymmetric model in the visualization module. Select the materials from the Color Code dialog toolbar to see the different material properties applied to the model with different colors. Note that the material properties were defined in the input files. You can sort the color code options in the pop-up window as you fit. See the model the top side of the threads is here and the bottom side is here. To refresh your memory, some calculations were made in the subroutine for the thread wear analysis for the tip of the thread edges. You can see the node numbers by selecting the common options, choosing the Labels tab and applying the Show Node Labels. Now you can see the node numbers of the top side of the thread and the bottom side, which were named NAdapt and NAdapt LAGR in the input file. Also, you can see the nodes with the Display Group tool. In the pop-up window, choose the nodes from the item, choose the NAdapt, then turn on the Highlight option. Now the nodes turn red. You can do the same for the NAdapt LAGR. You would be able to observe the results defined in the input files. You can see the stress, displacement, reaction force, and rebar force. Now let's go to the second ODB file, the revolve model. The axisymmetric section was revolved around the axis and became this model. Let's delete the node numbers for a better view. Note that the subroutine wasn't applied here. You can see the material properties with different colors as before. This is the same figure that we had in the PowerPoint. This line is the surface that the tire rolls over it. To see the whole surface from the View tab, select the ODB display options, choose the Sweep Extrude tab from the pop-up window, then extrude the surface. Now you can see the whole surface. In the third ODB file, the whole model is simulated in the Reflect model. We have a tire that rolls over a rigid surface. You can see the material properties with different colors, also stress displacement, and so on. The next ODB file is for the rolling model, which analyzed the model with a steady state step. You can see the outputs such as contact pressure and shear stresses error indicators here. Here we analyze the whole model with the steady state step. Compared to the previous analysis, this one presents more extensive results. If you remember, we defined a tire to roll over a surface for a distance of 32,000 kilometers with a speed of 32 kilometers per hour. The goal of the UMesh motion subroutine in this simulation is to analyze the tread wear during the tire movement. Note that we don't analyze tread wear yet. Now let's see the results of the tread wear analysis. We have two ODB files for this matter, one with slip and the other without. Here you can see the results without a slip and with a slip. The goal is to analyze and compare the tread wear amount before these three analyses: rolling model, model without a slip, and model with a slip. You can see the tread wear amount by the distance between two nodes. First, we need to create three viewports and align them vertically. The three viewports are the rolling model, the model without a slip, and the model with a slip. The two nodes where we mentioned earlier are the tire center and node number 97045. You could see the node position through the Query tool. Insert the node number here and the node turns red. Remember, the where that we applied with the subroutine is not just in the contact section between the tire and the rigid surface. And the where applies to the whole model. To refresh your memory, first all calculations were made for an axisymmetric model, then the model revolved, reflected, and the subroutine applied the where calculations to the whole model. Although we selected a region in the graphical view that doesn't have any contact with the surface, the subroutine is applied for the whole nodes. Also, the tire is rolling with a speed of 32 km per hour for a distance of 32,000 km, so the where is for the whole model. So let's find out the distance between the two nodes in the first viewport, the rolling model. From the Query tool, select the distance first, select the tire center, and then type the number 97045 here to select the second node. Here you can see the deformed distance or scale between the nodes, which is 3.1610⁻⁻1. The next model is the one without the slip. Again, select the distance, then the nodes, and this time the distance is 3.1510⁻⁻1. The distance is less than before, which means we had where in the thread due to the subroutine. Now let's see the last model. This model includes the slip. So let's check whether we have any where or not. Like before, selecting the nodes and checking the distance. This time the distance is 3.1410⁻⁻1. As we expected, the where is more than the last two models because the slip is considered in this model. If you want to see the thread edges in all models, first you should position the models in the same way. Start with the first model. Select the XZ plane. Click on the Create Display Group icon, choose Elements, then select Pick from Viewport. Click on the unformed shape so you can choose the elements easier. Choose half of the elements, click Done, and click on the Remove from the pop-up window. Now select the YZ plane and zoom it to see the thread edges. For the next model, do the same to see the thread edges. Do the same procedure for the last model to compare the results. If you look carefully, you can see the thread wear and the difference between the three models. Also, you can see and compare some results between them, such as stress, pressure, contact error indicators, and so on. Note that the mesh size might affect the error value. We have completed our analysis. Now you can understand how to use the UMesh motion subroutine in analysis like tire wear. So thanks for watching.